Good morning, everyone. It's good evening for me. It's my pleasure to be with you for a short while and talk briefly about the precision measurement of electric power and related quantities. This is the content of my talk. We'll talk about the standards of power and the standards for related quantities, and then make some conclusions. So, as Michael mentioned, I'm from Australia. Well, I'm currently in Sydney. You can see the aerial view of the National Measurement Institute. Only it's dark here now because it's 9 p.m. As every other National Meteorology Institute, our goal at NMIA is to make sure that measurements in Australia are reliable, fit for purpose, and internationally recognized. And we do it through a number of activities. First and foremost, we realize Australia's units of measurement, and we disseminate them to industry through accredited calibration and testing services. We support accuracy and support standardization, and we work through and with a number of international bodies, none the least of which is the International Bureau of Weights and Measures that organized this wonderful seminar. And I understand, I see already a lot of familiar faces, but I understand that the goal of our seminars is really to bring meteorology to a wider community, not necessarily people who work at National Meteorology Institutes and measure power every day. So this is what I think we'll try to do. And it will be an insult on everyone's intelligence to tell you just how important it is to measure power, particularly and measure energy, particularly in times when we want to save it. And sorry, I'm just hearing something. and try to move to the net zero economy. So this slide presents a typical traceability pyramid, where of course the SI units are at the top, and through primary standards and secondary standards, we provide traceability to measuring instruments in industry and commerce. And different levels of uncertainty are required for the different steps of this pyramid. So every science starts with definitions. So let us define power for periodic signal. And here we see an example of a sinusoidal signal, which do not really exist in reality. The power is an average integral of the instantaneous product of voltage and current over the period. And every periodic signal can be represented as the sum of harmonic sinusoidal powers. For the fundamental, the first harmonic, the power is simply voltage, RMS voltage times RMS current times the cosine of the phase angle between voltage and current, which we call power factor. But for non-sinusoidal signal, the power factor is really the ratio between active power and the apparent power. So we also talk about leading and lagging power factors for capacitive loads. Of course, when the current leads the voltage, the power factor is leading, and for inductive loads, it's lagging. Now, it's difficult to use, so a typical wattmeter would measure voltage across the load, and it would measure current across the load with the respective voltage and current circuit, and somehow provide the product, which is power. Of course, it's very difficult to use this particular configuration for calibration purposes, because the load dissipates real power, And if it is, for example, 1,000 volts and 100 amps, which is quite typical within the capability of the wattmeter, this would be 100 kilowatts. So it's very, very difficult to make an adjustable load for such power, and also environmentally unfriendly. Also, there's always some influence of the measuring circuits on the actual value, because as you can see from this diagram, some small fraction of the current through the load goes through the voltage sensing circuit of the wattmeter, and again, the current sensing circuit of the wattmeter makes a divider with the load. So there's always a non-zero effect from the measuring instruments when we measure active real power in the real situation. And that gives us enough ammunition to start talking about the standards of electrical power. And without exception now, the standards are organized in phantom power configuration. So there is a so-called phantom power source, which is two separate sources, one for voltage and one for current. And then the voltage and current circuit of the IUT is instrument under test are disconnected. And then what happens is we need to convert the voltage of the IUT typically to a smaller voltage or a smaller current that we can measure, and we convert the current of the IUT into a smaller voltage or a smaller current again, and then we use a low-level power comparator to compare it usually with DC that we know in terms of quantum standards. So using the power of quantum power source obviously minimizes the power dissipation. There's no hundreds of kilowatts, it's just units of watts maximum that are dissipated in the measurement circuits. That's quite clear. It's also clear that it's easy to set the test point. We can just adjust the voltage and current independently using very stable sources, and we can adjust the phase angle between the voltage and current. And there's no first order influence of the source on this measurement. I must say, there are debates now as to whether or not we can use this same phantom power configuration to test electric vehicle charging stations, because that would be advantageous, but then there's also some disadvantages about doing that, because then the meter, which is part of the station, may not be in the condition that the station is in. So this discussion is ongoing. So the requirements for the uncertainty are about 5 parts in 10 to the 6 at power frequencies, and for high frequencies, particularly now for hundreds of kilohertz, the requirements for the uncertainty are more modern. And later in the talk, I'll just be talking about those 3 main constituencies of components of the power standard: the voltage converter, the current converter, and the power comparator. Just one last bit of introduction with the formulas is that the correction for the standard is the combination of amplitude and phase correction in the voltage and current circuit, and the combined correction depends on the power factor. So if it's a totally active load test point, then the phase shift does not come in the correction, the phase errors, and only amplitude errors come into the correction, and vice versa. At 90 degrees, the amplitude errors don't matter, and this formula shows it to you. All right, so starting with the voltage converter, when I was thinking about this presentation, I wanted to say, I thought that at National Metrology Institute, really, we don't have many shots at developing things. So sometimes we only have one shot, so we try to do the best job possible. So as an example, at the National Metrology Institute of Australia, we use inductive voltage dividers for lower frequency, and then we use resistive voltage dividers at high frequencies. So this is the schematic, the appearance, and the laboratory to calibrate the NMI 1000 volt precision inductive voltage divider. It's one of the most accurate transformers in the world. And when people ask me just how to make a transformer with an uncertainty of 1 part in 10 to the 10th of input, what I'm saying is that if you really take a toroidal core and put a winding on it, then yeah, you can make a transformer, but it will probably have an uncertainty of 1% or 0.1% because of the finite magnetic permeability of the core. So what you can do is you can then put another winding on it, which is shown here, and then put a magnetic screen on it, and the best screen is the combination of copper and metal, and then you put your defining winding. So this is really the combination of 3 transformers, because the flux in the second core is only responsible for compensating for the error in the first stage, and the flux in the third core is responsible for compensating the error in the first 2. So if you have 3 transformers, each of them accurate to 0.1%, that's how you get a transformer that's accurate to 1 part per billion. And for the resistive divider, the best results that we've ever achieved was with really simple structure and a rather large box with minimized capacitive leakage throughout the circuit of the divider. And you can see the typical measurement results, the errors of such a resistive divider up to hundreds of kilohertz. You need a buffer to use with the resistive divider, and we've made made available to many our counterparts a 3-stage buffer, which again uses 3 stages each to compensate the error of the other, and this becomes quite an accurate and a buffer up to hundreds of kilohertz. And we're actually working now that we have sampling software to really make sure that the buffer has the part per billion accuracy that the theory tells us it should have. And the reason it sometimes doesn't have it is a microscopic amount of oscillation. And we are trying to extend the operation of this buffer to a megahertz. Now, for the current converter, we use current shunts. We make current shunts, which is a parallel combination of metal of thick film resistors calibrated against a calculable disc resistor in this N-type connector. And these are the typical AC/DC different curves of this shunt. And what I try to think is, on this scale, 1% is in the stratosphere. So these are quite accurate resistors, and we use them for measurements that require high bandwidth, but we don't quite use them for power frequencies and audio frequencies because there's no automation. For automation, we've developed a multi-range current transformer where the computer can switch primary windings and no shunts need to be changed during the measurements. So we can go from fractions of amp to hundreds of or 200 amps using a computer. And again, I like 3. The transformer has 3 stages, each of them accurate to 1%, compensating one another, just so that the total uncertainty is around 1 parts per million, which is confirmed by the typical measurement results that you can see here. So again, it's a 3-stage transformer. All right, now for the measuring device, I must say that practically everywhere or most NMI use sampling software, and in particularly, and we do too, and we also use a thermal power comparator as the primary standard. So I can't tell you just how nice is it to use the sampling software, which typically uses two commercial multimeters with without any external modification and without any external synchronization. And you know, the sampling software can produce lots of power and power quality parameters. However, when you look at, you know, a typical structure of the software, and I must say a free version of such software, which resulted out of a Euromed project, is available on the website that I'm referencing here. You can see that there's lots of things. There's filtering, there's digitization, there's Fourier transform. So this is, of course, not a primary standard in itself. So at NMIA, we use it, but we calibrate it using thermal voltage converters and the thermal power comparator on AC, and then on DC, we calibrate it using the electronic voltage reference, which in turn is traceable to the Josephson waveform synthesizer or to the primary Josephson standard. For the AC-DC difference that we obtain using the thermal converter is quite stable, but for best accuracy, we just calibrate the 2 meters in the sampling mode using the voltage reference. However, there is also work by very nice work by some of our counterparts where the Josephson standard is used directly to calibrate the meter and just bypassing the Zener, but we don't do it because this extra step does not bring much uncertainty in our case. Talking of uncertainties, you know, a typical NMI would prepare an uncertainty budget. So for us, it's about 3 parts per million at power frequencies. And then, of course, it goes higher as the frequency goes higher as well and reaches hundreds of parts per million at 200 kilohertz, which is the top uncertainty for us, at top frequency for us at the moment, although we are working to extend it to a megahertz, as I said. There are many parameters that are related to electric power. One of them, of course, is the phase shift. And I'm showing this diagram just to say that at the uncertainties of microradians, it's not really possible to use zero crossing to measure phase shift. So you need something that really measures the power factor or does the Fourier analysis. So thermal standards or sampling standards are the way to go. And we just use 2 inductive voltage dividers of the kind that I've shown to measure phase. And that gives some very nice CMCs that peers around the world have approved. We also use Josephson standard to generate complex signals with known phase and amplitude. And the beauty of that is that an arbitrary waveform that is useful for our users in energy, that helps support renewable energy, can be generated to the nth degree to the quantum precision using a Josephson arbitrary waveform synthesizer. And the group of we use the NIST Josephson arbitrary waveform synthesizer. And actually, just this week, NIST colleagues are here in Australia to install the new generation standard with much larger voltage, and that achieved a technical award from the Instrumentation and Measurement Society, and again led to some very reasonable specifications. And finally, just to end on a high note, I'd like to go to the high voltage, where it's also becoming really important to measure harmonics and particularly measure power with composite signals that contain the fundamental and contain an arbitrary content of high voltage and high current harmonics up to 10 kilohertz. So, you know, the harmonics are really beginning to penetrate not only to distribution networks, but also to the transmission networks. And knowing their propagation, to know their propagation and to mitigate that requires measurement. So that's what we have developed to support this process. So here's, for example, a diagram of the harmonic voltage calibration system, and that contains a composite source that can provide a 100,000 volts of fundamental frequency plus 1,000 volts of harmonics up to 10 kilohertz. And then we use the same techniques really to calibrate the capacitive divider, which is the reference for the high voltage harmonic system. And we already started calibrating voltage harmonics, voltage transformers, and also current transformers. There's a similar system up to 4,000 amps, where 1,000 amps would be harmonics that are the exact replica of what one can find on the network. So the fundamental power standards and developing of all these precision devices really helps to achieve traceability and really support renewable energy and support energy efficiency even at much higher voltage than at much higher currents. So I believe this is all the time that I had for my talk. So to conclude, I can just say that precision measurements of electric power are really important to support trade. And these days, they're really important to support transition to net zero. And most of us at National Metrology Institutes have established primary standards with, I would say, staggering degree of precision, with uncertainties of parts in 10 to the 6, at least at power frequencies. And we are working to improve these standards, both in their accuracy, but also in the range of quantities that we can measure. So I'll probably end my talk at this, and if there's time for any questions, I'll be happy to tackle it.